In today's lecture, we are going to start our journey of simple ionization. In this lecture, we will learn the principle and components of electron ionization, chemical ionization, atmospheric pressure chemical ionization, and atmospheric pressure photoionization. Simple ionizations can be classified as the hard ionizer or soft ionizer. Hard ionizers can produce ion with a great deal of excess internal energy leading to fragmentation, which is less likely to produce the molecule ion N+. On the other hand, soft ionizers produce considerably less fragment ions and are very likely to produce the molecule ion or quasi molecule ion. A quasi-molecule ion is an ion formed by the association of the molecule M and the non-charged species NH+ or N-sodium plus. This figure illustrates the spectrum of ionization techniques. Electron ionization is an important technique for analyzing low to medium polarity non-ionic organic compounds of molecule weights in the range of up to 800 U, which formally has been referred to as electron impact ionization or simply electron impact. In electron ionization, the energetic electrons are shot onto a gaseous neutral to affect their ionization. When the neutral is hit by an energetic electron carrying several tens of electronvolts of kinetic energy, some of the energy of the electron is transferred to the neutral. If the electron, in terms of energy transfer, collides very effectively with the neutral, the energy transfer can exceed the ionization energy of the neutral. Then the electron may be ejected from the molecule ion, forming positive radical ions, which can be even or odd electron ions. Electron ionization predominantly creates a single charge ions from the precursor neutrals. If the neutrals was a molecule, as in most cases, it started as having an even number of electrons, or a closed-shelled molecule. The molecule ion formed must be a radical, cation, or an odd electron, or open-shelled ion as these species are termed. In a rare case, the neutral was a radical. The ion created by electron ionization would be even electron, for example, for nitric oxide. The EI mass spectrum of the anthropoline derivative shows a series of comparatively intense doubly charged ions, the one at 178 being the doubly charged molecule ion. The others represent the doubly charged fragment ions. The occurrence of doubly charged ions of moderate abundance is quite common in the mass spectra of polycyclic aromatic hydrocarbons. This figure illustrates the possible processes under electron ionization conditions. Electron capture is rather unlikely to occur with electrons of 70 electron volt since EC is a resonance process. No electron is produced to carry away the excess energy. Electron capture only proceeds effectively with electrons of very low energy, preferably with thermal electrons. The ionization energy is defined as the minimum amount of energy that needs to be absorbed by an atom or molecule in its electronic or and vibrational ground states in order to form an ion that is also in its ground states by ejection of an electron. Ionization energies of most molecules are in the range of 7 to 15 electron volt. Removal of an electron from the molecule can formally be considered to occur at a sigma bond, a pi bond, or at a lone electron pair. The sigma bond being the least favored and the lone electron pair being the most favored position for charge localization within the molecule. An assumption directly reflected in the ionization energy. These tables summarize the ionization energies of common compounds, where you can see the saturated, the carbon-hydrogen bonds or inner gases are with the greater ionization energy. Electron ionization can be represented by a vertical line in this diagram. Those ions are formed in a vibrationally excitation state if the internuclear distance of the ionization state is longer than in the ground state. Ions having internal energies below the dissociation energy D remain stable, whereas the fragmentation will occur above. In few cases, ions are unstable. There is no minimum on their potential energy curve. The lower part schematically shows the distribution of Frank-Condon factors FC for various transitions. The probability of a particular transition from the ground state neutral to a certain vibrational level of the ion is expressed by its Frank-Condon factor. The Frank-Condon factors originate from the fact that the probability for a transition is highest where the electronic wave functions of both ground state and excited states have maximum overlap, while for the ground state this is at equilibrium position. The wave functions of higher vibrational states have their maximum at the turning points of the motion. The larger R1 is, as compared to R0, the more probable will be the generation of ion excited even well above the dissociation energy. No matter where the electron has formerly been taken from, ionization tends to cause weakening of the bonding within the ion as compared to the precursor neutral. Weaker bonding means longer bond lengths on the average, and this goes with a higher tendency towards the dissociation of a bond. Bond breaking is an endothermal process, and thus the potential energy of the fragment ion is usually located at a higher energy level. In fact, the ions are not generated by one specific internal energy applying for all ions, but via a broad energy distribution (PE). However, such a distribution is only valid for a large set of ions as each individual one bears a defined internal energy ranging from just above IE to well beyond 10 electron volts for certain ones. Fragmentation of those highly excited ions from the tail of the PE curve yields fragment ions having still enough energy for a second dissociation step, or even a third one. Each of the subsequent steps can, in principle, also be characterized by an apparent energy value. The conventional electron ionization instrumentation includes a sample reservoir, a source housing, a filament that can produce ionizing electrons, a trap electrode, a repeller that can push out the ions towards analyzer once they are generated, and a focus plate and accelerating field, a heater, and a weak magnetic field. The sample introduction system can be divided into three classes: reservoir inlet, direct insertion probe, and the chromatograph. These sample introduction methods are of equal importance to other ionization methods. Here are the photos for sample reservoir and direct insertion probe. The principle and the analyte suitable for each inlay system are summarized in the table for your reference. The gas or vapor being analyzed enters the ion source of the instrument and is converted to ions. The electrons are emitted by a direct heating cathode made of a multi-purpose wire, and the direct current volt of 70 electrovolt is applied between the ionization chamber, like positive electrode, and the cathode, the negative electrode, to accelerate the electron into the ionization chamber. When these electrons bombard atoms or molecules in gas in the ionization chamber, the atoms or molecules lose the electrons into the positive ions or molecular ions. The molecular ions continues to be bombarded by electrons, making some chemical bonds to break or causing the rearrangements to break into multiple fragment ions or positive ions at an instantaneous rate. But why using the 70 electron volt? This is because the experimental data shows that the maximum number of ions produced are at about 70 electron volt. Low energy primary electrons limit the excess energy deposits onto a molecular ion. Using the 12 to 15 electron volt instead of 70 electron volt still ionize most compounds, while disadvantageous fragmentations are reduced. Superior EI mass spectra of large hydrocarbons can be obtained, even more so if the ion source is operated at 70 Celsius degree instead of 200 Celsius degree. Low energy, low temperature mass spectra are much easier to interpret than their conventional 70 electron volt counterparts for several reasons. First, the relative intensity of the molecular ion peak is enhanced, thus permitting this important peak to be identified more easily. Second, less fragmentation also means a simpler overall appearance of the spectrum. Third, the fragmentation pattern is dominated by a few characteristic primary fragmentation, carrying a large portion of the structural information. However, there are also some disadvantages of using low-energy electron ionization, such as loss of sensitivity and carryover effects. Nonetheless, during the first decades of analytical mass spectrometry, low-energy EI spectra were the only way to minimize fragmentation, and thereby to increase the relative intensity of a weak molecular ion peak. Nowadays, EI mass spectra are preferably complemented with spectra obtained from so-called soft ionization method, which we will introduce in the following content. This is another example of the low-energy EI mass spectra for beta-lactam. The mass spectra become cleaner and retain the larger molecular ion peak when using the 15 electron volt energy. Analyte should be able to evaporate or sublime without significant thermal decomposition. For example, saturated and unsaturated aliphatic and aromatic hydrocarbons and their derivatives such as halides, ethers, acids, esters, amines. GCEI mass combination is especially successful in monitoring the environmental pollutants such as polycyclic aromatic hydrocarbons, polychlorinated biphenyls, or polychlorinated dibenzodiazine, polychlorinated dibenzofluorans, and other volatile organic compounds. As EI mass spectra are excellently reproducible when measured under standard conditions, the databases have been developed using the EI mass spectra. The most comprehensive EI mass spectral databases are the NIST mass spectral database and the Wiley mass spectral database. The latest NIST EI mass library was released in 2020, containing over 350,000 EI spectra. To sum up, electron ionization is well established, having existing fragmentation libraries for structural elucidation, null suppression, and can be applied to insoluble samples, easily interface to GC, suitable for nonpolar samples, ease of operations, and lack of the contamination issue. Nevertheless, electron ionization also exceeds several disadvantages, including the difficult for parent identification, requiring volatile but thermally stable sample, only suitable for low mass compounds, and the fragmentation complexity. Next, let's talk about chemical ionization. Chemical ionization technique is especially useful when no molecular ion is observed in EI mass spectra of a compound, and also in the case of confirming the molecular weight of a compound. CI technique uses nearly the same ion source device as in EI, except CI uses tight ion source, a reagent gas, and a higher energy of the primary electrons to penetrate the reagent gas. Chemical ionization is based on ion-molecule reactions, may involve the transfer of an electron, proton, or other ions between the neutral analyzed M and the reagent ions generated from the reagent gas. CI generates analyte ions via bimolecular processes requiring a sufficiently large number of ion molecule collisions during the dwell time of the reactants in the ion source. To accomplish these massive collisions, CI usually increase the partial pressures of the reagent gas. Greater reagent gas pressures can also effectively shield the analyte molecules from direct ionization by primary electrons in order to suppress competing EI of the analyte. Most CI techniques deliver even electron-positive analyte ions via four fundamental pathways: proton transfer, electrophilic addition, anion abstraction, charge transfers as described with the corresponding molecular equation from 1 to 4. Few other conditions may occur during the chemical ionization, including the negative ion chemical ionization and electron capture. Negative ion chemical ionization refers to the technique that delivers even electron negative analyzed ions. Electron capture, strictly speaking, is not a CI technique, but the ion source operation is equal to NiCi. As we previously mentioned, traditional chemical ionization requires additional pressure to facilitate the ion molecule collisions. However, atmospheric pressure ionization, or API, refers to the technique that can achieve ionization under ambient pressure. Say if we have a solution containing our molecule ions and solvent ions, API typically apply a drying gas to evaporate the solvent ions. The charges within the droplet become closer to each other, generating the repulsive force and forming a smaller droplet. At the same time, the molecule ions and solvent ions maybe collide with each other and enabling the chemical ionization. This diagram shows the internal structure of an API source. The ionization is operated under the ambient pressure 760 On the other hand, the mass spectrometer is operated under vacuum or low pressure to avoid the unnecessary interactions between ions. In addition, the ionized molecule from the ionization source can be directed to the mass analyzer. APCI is a similar technique with CI. The key difference is that APCI can be operated at atmospheric pressure. APCI can be used for analysis of compounds with molecule weights up to 1,500 Dalton and can generate monocharged ions. The APCI usually can couple with the liquid chromatography system. Once the LC eluent get into the source, the droplet will undergo ion evaporation steps, forming a smaller droplet and ultimately charged ions. The nebulizer consists of three concentric tubes. The eluent is pumped through the innermost tube and nebulizer gas and mega gas through the outer tubes. The combination of the heat and gas flows dissolves the nebulized droplets, producing dry vapor of solvent and analyte molecules. The solvent molecules are then ionized by a corona charge. The results of these reactions produce water cluster or protonated solvent, which can further initiate the chemical ionization. This is a diagram to illustrate the different setup of the APCI interface. On the left is the parallel setup that aligns a nebulizer tube, a corona discharge needle, and a mass analyzer together. On the right is the Agilent design that the nebulizer inlet is in the perpendicular position compared with the corona discharge needle and mass analyzer. This setup is more selective and thus reduce the background signals. Using different solvents may result in different reagent gas ions. This table summarizes the possible reagent ions in positive ion direct liquid introduction LC mass when using 1:1 water and methanol as the mobile phase. The reagent get ions includes the 15, the CH3, 18, H2O, 19, H3O, and protonated methanol, protonated dimethyl ether, etc. If we use one-to-one water and acetonitrile as the mobile phase, we would have a totally different profile for reagent ions such as 40, CH2CN, 42, CH4CN, protonated acetonitrile, etc. The positive charged reagent ions can further initiate the chemical ionization. If you add ammonium acetate in your mobile phase, you would expect to obtain the reagent ions with ammonium adduct. In other words, if we only inject 20% methanol in 50 millimolar per liter ammonium acetate, we still can observe lots of peak in the acquired mass spectrum, and these positively charged adducts can also initiate the chemical ionization. Drying gas or nebulizer gas is critical in assisting the ionization process. The drying gas can help to get rid of water, facilitating the ion evaporation, and enhance the ionization efficiency. API source usually coupled with a vacuum system. Despite the different configurations, the rule of thumb is that the ionization is operated under ambient pressure, and the mass analyzer has a vacuum system to direct the ions passing through. The low pressure in the mass analyzers can avoid unnecessary collision among ions. APCI has similar reaction modes with CI, including the proton transfer, adduct formation, charge exchange in positive ion mode, and proton abstraction, anion attachment, and electron capture in negative ion mode. As the LC mobile phase solvent is usually with higher proton affinity, the mobile phase additives play important role in the ion molecule reactions. This slide summarizes the strengths and limitations of APCI. APCI usually can retain the molecular ion peak and achieve a higher ionization efficiency compared with traditional chemical ionization. Compared with electrospray ionization, APCI is relatively insensitive to salts and can handle high flow rate. The limitation of APCI is that it is more suitable for volatile and thermally stable compounds. Atmospheric pressure photoionization (APPI) was firstly introduced in 2000 as a complement or alternative to APCI. In APPI, a UV light source replaced the corona discharge-powered plasma, where a quartz tube is used to guide the hot vapor towards the sampling orifice. Photoionization of analyte molecule is neither energetically or statistically favored process. Molecule AB can undergo photoexcitation when absorb photon energy with a light frequency of mu, leading to the following consequences: radiation decay, photodissociation, or neutralization. The excited AB molecule can return to the ground state, AB, releasing the absorbed energy H mu, or undergo photodissociation to form radical A and radical B. Even if ions AB plus radicals have formed, they can be lost by neutralization via the recombination with free electrons present in the plasma. Eventually, along with moderating ion-neutral collisions. This figure illustrates the relationship between UV lamps and the ionization energy of a compound. The compounds can form an ionized species only when the UV lamp provides sufficient energy to overcome the ionization energy. We mentioned that the photoionization is not a favored process. Instead of relying on direct photoionization to occur, one normally would prefer a chemical ionization process where the reagent ions are formed by photoionization of a reagent gas. In the case that the solvent cannot be photoionized by the UV lamp, we can add the UV absorbing dopant to facilitate the chemical ionization by charge transfer, as explained in these equations. The excited dopant ions may directly lead to the formation of molecular ions or the solvent reagent ions. Methanol, for example, cannot be ionized by use of a krypton lamp, but addition of some acetone as dopant will allow the process described in equation A, B, and C to occur. Overall and in general, much of what happens in APPI bears close resemblance to APCI and CI, while the role of direct photoionization for aniline ion formation is less pronounced than suggested by its name. The ionization energies of the commonly used solvents are summarized in this table. The considerations of appropriate solvent is critical in APPI experiments. Usually the solvents need to be compatible with the UV lamp. In other words, we would prefer the formation of solvent ions to embark the chain of chemical ionization. As the principles are similar between APCI and APPI, a dual ionization source has been developed by many companies. The users can switch the ionization mode using the same instrumentation in these days. This diagram illustrates the three most commonly used ionization techniques in the modern LC mass analysis, which covers the analysis of nonpolar compounds to highly polar compounds. From today's lecture, we already introduced the APPI and APCI. In the next lectures, we will talk about the electron spray ionization, ESI.